thank you very much for the introduction, and thank you very much for allowing me to talk here today. So I'm a PhD student in Versailles, at the University of Versailles, under the supervision of Aline Bostan and Lucia Divizio. And today I will present to you a joint work with Florian Fürnsinn from the University of Vienna. And this work is now a preprint on arXiv that you can have free access. Okay, so first I will tell you a bit about the introduction to the topic. So we are interested in functional equations and their solutions. And so first we want to define what is a solution to an equation. And we will consider formal power series, such as this one, with rational coefficient most of the time in this talk. And here you can see with this, in this rectangular form, that there is written rational, not because of the rational coefficients, but because such a formal power series can coincide with the Taylor series development of a rational function. But that is maybe a too restrictive property, and so we are interested in other properties of a formal power series, namely algebraicity. So a formal power series is algebraic if it satisfies a polynomial equation with polynomial coefficients, just as in the case of numbers. Very easy examples are rational powers of polynomials. They obviously satisfy a polynomial equation. And so, of course, rational power series are examples of algebraic power series. We have another notion, which is D-finiteness, and we say that a power series is D-finite if it satisfies a linear differential equation. And examples are exponential of polynomials that satisfies first-order differential equations. And well, the interesting thing about these two properties that I just defined is that we have a theorem due to Abel that states that all algebraic series are D-finite. So this theorem is not only interesting because of this result, but also because of its proof, because its proof is effective in the sense that given a linear differential equation, it allows us to compute, given a polynomial equation, it allows us to compute step by step, or with a computer, the linear differential equation satisfied by the solution of the polynomial equation. Okay, so with the two examples we had before, well...
I don't agree with this. The exponent of x0 plus 1 doesn't have rational coefficient.
Doesn't have rational coefficient.
The exponent of x1, which is not rational.
Sorry?
Because you have exponent of 1, which is not rational.
We have
it's the exponent of x squared plus 1.
Yes.
See, is that from e exponent, e1, exponent of 1?
Yes, it's true. So it should be just x squared.
Yeah,
thank you.
Yeah.
Okay. Thank you very much. We know that this power series here is D-finite because it was algebraic for what was here just before. And conversely, well, if we just take the exponential of x squared, we know that it is not algebraic, so the converse of the theorem of Abel is not true. Okay, so now our question will be to quantify what is, to try to answer to when the converse of Abel's theorem is true. And so given a D-finite power series, we want to decide if it is algebraic. And by decide, we mean that we want to have an algorithm that doesn't let us think about the solution, but we just want to write the differential equation, ask the computer, and the computer will tell us if it is algebraic or not. Okay, so this problem of deciding algebraicity of solutions of differential equation was formulated by Fuchs in the following terms. If we consider a linear differential operator L, then Fuchs' problem is to decide if the differential equation associated to the operator L has a basis of algebraic solution, that is, as many linearly independent algebraic solutions as its order. So here it is n. And a related problem was formulated by Abel, or at least it is known as Abel's problem. And it is the same problem, but for first-order linear differential equations with here a coefficient that is no more necessarily rational, but it can be algebraic over Q of x. Okay, so these two problems were studied, and an answer to Abel's problem was given by what is now called Risch's algorithm, due to work by Risch, but also many other people, and many people that do not fit on this slide. And in 1980, Singer gave an answer to Fuchs' problem by an algorithmic answer relying on Risch's algorithm, but unfortunately, the computations involved in Singer's algorithm are not cannot be made by today's. So they are too big, and so they cannot be made by today's computers. So,
just for knowing a bit about the history of that, if you allow, is the Fuchs problem when Fuchs stated it? I mean, is it in that terms, or it just phrased in this way by modern thinking? So when was the Fuchs problem? Do you know?
I do not know. I would expect it to be at the end of the 20th century, but
okay.
I'm not sure.
Okay, so it's really a decision problem associated with that problem. So okay.
Yes. Yes. So Fuchs' problem is not necessarily a question of having a computer, obviously, because Fuchs was born before computers.
They were doing the computation, so they care really for having efficient stuff. Because you do it by hand, so you need the good algorithms, in fact.
Mm-hmm.
Okay. Thank you. And so we will have another approach to this problem, which will be a local global approach. That is, we'll try to reduce our question to questions in characteristic P. So if we consider a differential operator, just as before, and polynomial coefficients, well, for any prime number P, we can consider the differential operator associated, so over Fp of x, given by the reduction of all the coefficients modulo P. So we obtain in this way infinitely many new differential equations associated to these differential operators Lp here. Okay, there is a conjecture due to Grothendieck that predicts a local global behavior in the algebraicity of solutions. So it states that so Grothendieck predicts that in characteristic 0 there is a basis of algebraic solutions if and only if the same thing happens for all over Fp of x for all prime numbers P. So now what we might, okay, so just a bit of history about this conjecture. So it was stated by Grothendieck, and then it was proved for different kind of equations, but actually it's very open. And what will be interesting in today will be the order 1 case of Honda. Okay, so sorry, I was a bit too fast. So the thing is, we wanted to decide something, so we want to have an algorithm to decide the algebraicity of solutions over Q of x. And now we have reduced this to checking the algebraicity of solutions for infinitely many new equations. So that's the first problem. We now have infinitely many conditions to check. And the second question we might ask is, why would it be easier to check the existence of a basis of algebraic solutions over Fp of x, so in characteristic P, whereas before we were in characteristic 0. So the answer to the second question is that there exists there exists an Fp of x linear map that I will not define that we can attach to the differential operator Lp. It is called the p-curvature, and the only thing we need to know actually is that we can compute it first, and second that it is an n by n matrix where n is the order of the equation. Okay, and the reason we're interested in this p-curvature is that it encodes in some sense, the algebraicity of the solutions. So the p-curvature of Lp vanishes if and only if the differential equation has a basis of algebraic solutions over Fp of x. So this is known as Cartier's lemma, and this allows us now to restate Grothendieck's conjecture, but by changing the local condition by replacing having a basis of algebraic solutions by having a p-curvature that vanishes. So this is what is known as Grothendieck's p-curvature conjecture. Okay, so I will give a very last motivation to this problem, which is indefinite integration in the inhomogeneous case, because in the rest of this talk we'll be only interested in first order differential equations, but homogeneous ones, so y prime equals u times y. And right now I want to have a look at what happens for y prime equals u when u is a rational function. So we want to decide if this solution, so this primitive of u, is algebraic. Well, this is a mystery to probably no one in this room, that this power series, the primitive of u, is algebraic if and only if all the residues of u are 0 in its partial fraction decomposition. And this happens to be something we can check algorithmically, thanks to this theorem proved independently by Rothstein and Trager. So if we have a rational function, u of x, so we can compute its partial fraction decomposition. So we can, okay, by hand, we know that it has a partial fraction decomposition of this shape, f prime plus a sum of residues over simple poles. And then we know that the residues are exactly the roots of a polynomial that we can compute as a resultant depending on a and b, the numerator and denominator of the rational function u. So this allows us to answer positively, to answer to the problem above in the case of inhomogeneous differential equations of first order, of course. We can decide with a computer by computing this polynomial and then having a look at its roots. So we just want to check that this polynomial is the power of x, in which case all these residues will be 0. So we can answer this question with a computer. So now what happens for first order differential equations, but now in the homogeneous case. So we consider this equation with u of x, just as before, we will write its partial fraction decomposition as a derivative of a rational function plus a residual part. And this residual part, so it has poles and residues that are algebraic numbers. We know that a non-zero solution of this equation is given by the exponential of a primitive of its coefficient, and so we can rewrite it in these terms. And we know that here we have an almost polynomial part, except that the alpha i's are not necessarily integral, but they are algebraic. And we have an exponential. So I will not give, so what I will say right now is actually proved with theorems that are, okay, we can prove it either very elementarily or with very high-level number theoretic theorems, but we know that we do not want this exponential part because if this is non-zero, well, we will always have an transcendental, so a non-algebraic power series here. So we want actually u of x to have this shape to only be the sum of residues over simple poles. Okay, now what happens in the case of characteristic p? We know that in this case, and only in this case, we have a closed formula for the p-curvature due to Jacobson, and which is this one, the p minus 1's derivative of the coefficient plus its p's power. And so we can compute, in the case of this coefficient u, the p-curvature of the equation. And so we see that we have a sum well, we have a denominator here, but what's interesting is this numerator, because for almost all primes p, if we want the p-curvature to vanish, we actually want every of these numerators to vanish. And we know that this happens if alpha I modulo p is in fp. So if we compare the two solutions, the two things that we have, first we had here a solution that we want to be algebraic. So and we know that this is algebraic if alpha I are all rational number, in which case putting it to the appropriate exponent it will become a polynomial. And we know that if alpha is algebraic, this is never rational. This is never algebraic. And in the case of characteristic P, we want these p-curvatures to vanish. And we know that this happens if alpha i's modulo P are in Fp. So we get conditions on alpha I in characteristic 0 that they are rational, and alpha i's in characteristic P that they reduce modulo P. Okay. That they reduce modulo P to in Fp, sorry. Okay. And so we know that these two conditions are equivalent thanks to a theorem of Kronecker. So first, I just rewrote the theorem of Rothstein-Trager because just to ensure that we can compute these alpha i's. So we can compute actually annihilating polynomials for these alpha i's. And second, the theoretical answer to the problem is this theorem of Kronecker that is exactly the local global principle that we were looking for. So if we consider a polynomial R of W with rational coefficients, and that is irreducible, then if for almost all prime numbers P, the polynomial R of W modulo P has a root in Fp, well, we know that R of W has a root in Q, and hence it is linear. So it is exactly saying that if alpha I modulo P reduces to Fp for almost all primes P, then alpha was a rational number. Okay. So this was actually the proof that Honda gave of the Grothendieck's conjecture for the first order homogeneous case. So we consider this equation the same as before, and the Rothstein-Trager resultant, which roots are exactly the residues of U. In characteristic 0, we have the equivalence between the equation having algebraic solutions and some conditions on U, that is having the form that I showed before. So this is encoded in the degrees of numerator and denominator and having simple poles. And we also want R of W to split completely in Q of W, so that we know that all residues are rational. In the characteristic P case, we have these three equivalent conditions. So first, the two same as before, and third, the vanishing of the p-curvature. Okay, and now Kronecker's theorem. Kronecker's theorem tells us that 2p for almost all prime numbers P implies 2. And so from this, Honda tells us that 1p for almost all prime numbers P implies 1. Okay, so we have tackled one problem, which is solving theoretically, let's say, the local global question we had. But now what we want is to deduce this characteristic 0 property from this property in characteristic P, but now for a finite number of prime numbers, so that we can really compute everything on with a computer. Okay, so before going further, let me give examples of what we just said. If we have a look at this equation, y prime equals y, well, it has no solution in power series in Fp. And we know that in characteristic 0, the exponential of x is transcendental. Okay, so indeed, if we compute the p-curvature, well, it is always 0. It is always non-zero. And so this can maybe convince someone that it's not completely absurd. Another example is if we consider the exponential of the arctangent, well, it satisfies this first order differential equation in characteristic 0. And if we compute the p-curvatures, well, for half of primes it is 0, and for another half of primes it is non-zero. And so we know, just because for p equals 3, for instance, y of x is not algebraic. Okay, because for it is not 0 for almost all prime numbers. Okay. Okay, so now let's go to our contribution with Florian Fürnsinn. It is based on the following theorem of the Chudnovsky in 1985. So they proved an effective version of Kronecker's theorem that could answer our question today. So if we consider a polynomial with a leading coefficient that we write delta, then there exists a bound sigma such that R of W splits completely in Q if and only if R of W modulo P splits completely over Fp. And we know for which primes we want to check that. It is for primes not dividing delta and at most sigma. So we have a finite number of primes for which we have to check our condition thanks to the Chudnovsky. But actually they did not give an expression of this sigma, and so our main contribution with Florian and Fürnsinn is to give an expression for this sigma. So I gave here expressions of all the parameters, but really what we want to know is that we can choose sigma equals a specific value that we can compute. And a remark that I want to say on the theorem of the Chudnovsky is that it gives actually a criterion of transcendence, because if for one single prime p not dividing delta and at most equal to sigma, we have a non-vanishing p-curvature, then obviously R of W will not split completely in Q. So we just need to prove that R of W does not split completely. We just need to check that it is true for one prime number, well-chosen prime number. Okay. I will try to give a hint of the proof, which is based on Hermite-Padé approximation. So that was the main idea of the Chudnovsky. So Hermite-Padé approximation is the idea is to approximate some given power series. So we want to find some polynomials pi's with a constraint on their degrees, such that the linear combinations of the pi's and the fi's have a certain number of vanishing first coefficients. And if we do a bit of linear algebra, we can consider the pi's to have indeterminate coefficients. And this gives us a linear system of r times n plus 1 indeterminates and s linear homogeneous equations. So we can always choose s to be at least equal to r times n plus 1 minus 1. So this is always possible, and this will appear in the proof. So this tool of Hermite-Padé approximation was introduced by Hermite in 1873, and it was already to prove a transcendence result, that E is transcendental. And then the study, the general study was pursued by Padé. So he was a Hermite student. So I wrote just one date, but it's actually in 1894 and afterwards. Okay, so the idea to prove algebraicity will be the following. We take one power series and all its powers. And we want to say that f is algebraic if for some optimal pi's, then the remainder of the Padé approximation vanishes, not only up to the order s, but actually it completely vanishes. So that's what we want to prove today. So I'll try to give a hint of the proof. So if we take a irreducible polynomial R of W that has a root in Fp modulo almost all prime numbers P, we want to prove that, so we assume what I just said, and we want to prove that it has a root in Q. So we assume that it has a root alpha that is not in Q. And we'll prove that it is absurd. We write L this field, and we know explicit Padé approximations to these powers 1 minus z to the alpha. And so we can compute this remainder. We know explicitly what are the p0, p1, p to the 2m. And we know explicitly what is this g. And sigma is so the order of vanishing. So sigma depends on the parameters, so the degrees of the pi's and the order of the Padé approximation scheme. And g is just this rational number that is non-zero. And just to give you a hint of what appears in the pi's, in the explicit expressions, it is this kind of binomial coefficient, so the inverse of this kind of products of binomial coefficients. And so what's interesting here is we really see that if alpha was rational, we could not put such a Padé approximation scheme because this would vanish at some point. Okay. To conclude the proof, we will rely on the following well-known inequality that is in any number field. If we take a non-zero algebraic number gamma, the appropriate power of its denominator times its norm is an integer, and so it has absolute value greater than 1. Now, the idea of the Chudnovsky was to produce a sequence of gammas depending on the parameter m and the parameter n, such that this quantity for gamma will decrease to 0, and so at some point it will be smaller than 1. So that's exactly what is written here. If we take n and m large enough, we obtain at some point this inequality that is absurd unless gamma mn was 0. But we know it's non-zero, so our assumption that alpha was non-rational is absurd. Okay, so now our question of effectivity became to quantify, to give upper bounds on values of n and m for which this inequality was satisfied. Okay, and so it's very technical and it's not very interesting to go into the details, but we did that. So now we can rephrase our previous theorem just in terms of differential equations. So this is not, okay, it's really just what was on the slide of the Chudnovsky theorem. So if we take a of x and b of x to be two coefficients of our differential equation, we can compute its Rothstein-Traeger polynomial, and then we have a certain number of parameters such that, and here is the interesting part, all solutions of the differential equation here are algebraic if and only if the p-curvatures of the equation vanish for all primes p not dividing delta, and at most sigma with an explicit computable value for sigma. Okay. Okay. So, okay, I did not know I had this slide. So, the interesting thing also is that there is an alternative approach that we could think of that is a bit more theoretical, because maybe you had noticed that when I stated Kronecker's theorem, well, of course it is due to Kronecker in 1980, but the usual proof of this theorem is due to Chebotarev. It's a consequence of his density theorem. And so we know that there exist effective versions of Chebotarev's density theorem, and so one can wonder if they can be of help to bound the first prime for which something happens. So here, the first prime we want to bound is the following. So we have we consider a polynomial R with a leading coefficient delta, and we consider L its splitting field over Q with discriminant D, and N the degree of the extension. Then we know that the smallest prime P such that R mod P does not split completely in Fp is exactly the smallest prime P that does not split completely in the extension L of Q. And so from this, our question of checking the vanishing of a polynomial, our question of bounding the first prime for which a polynomial does not split completely in Fp becomes the question of finding the smallest prime that does not split in a given number field. There exist bounds for that. This is an effective version of Chebotarev's theorem. So there are conditions, but there are conditions on D and N. But we know then that there exists a prime P such that P does not split completely in L, and P is at most equal to this bound. So there exist many versions. Actually, I just put one of effective Chebotarev just to give you a hint of what could happen. But our main problem with having, if we wanted to have an algorithm out of this theorem, would be that in general we have a polynomial R that is given as the Rothstein-Traeger polynomial of two polynomials A and B, and we do not know exactly how its discriminant or how its how any invariant of the polynomial will relate precisely to the discriminant of the number field, because here we have D, the discriminant of the number field, and we are not quite sure how to bound have to have a bound on D given just the polynomial R. Okay, so D is the discriminant of the splitting field of R. So this is a possible theoretical approach, but in practice we could not use this one. Okay, so now what we indeed did was, after we proved a refinement of the Chudnovsky theorem, we indeed implemented an algorithm that is available in Sage Math. So the algorithm is the following. We have as input two polynomials a and b that are the coefficients of a differential equation. We already asked that it satisfies a certain number of constraints. And as output, we want to have the nature, either algebraic or transcendental, of the solutions of our differential equation. So first we compute the Rothstein-Traeger polynomial and all necessary parameters. Okay, and so we obtain this sigma, which is the bound up to which we want to compute the p-curvatures. And we initialize p at 2, then we compute all p-curvatures up to p equals sigma, unless p divides delta, in which case we just skip this prime number p. And whenever we have one non-vanishing p-curvature, then we can immediately return transcendental. And if we end this loop without having found any non-vanishing p-curvatures, well, we can conclude that the solutions of our differential equations are algebraic. Okay, so I'll try to have a look a bit at the complexity of this, because this is an algorithm, but can it run on a computer? So our inputs are the degree of our coefficients and the height of their integer coefficients. So we have n and h. Computing all these values, so namely the Rothstein-Traeger polynomial, but also all this, can be made in O tilde of n squared log h bit operation. So O tilde just hides logarithmic factors, but what you can just remind, if you're not familiar with this, is just it is polynomial in n and log h. Okay. Now the thing that might be difficult was computing p-curvatures, but we have an algorithm of Bostan and Schost to do so, and it allows us to compute. So it's an algorithm that is very efficient for computing first order, so p-curvatures of first order differential equations. And so here we see that we obtain a complexity for computing all these p-curvatures in O tilde of n squared times sigma bit operations. And now our problem is we had two parameters in input, n and h, and now we have a sigma, so we need to estimate it. And sigma happens to be exponential in n and log h, something which we do not like at all, because then we obtain this complexity. So we can expect this algorithm to be very highly non-efficient. Okay, but I'll say a bit about actual computations in a minute. Another approach that is possible, well, you might say, okay, we computed a Rothstein-Traeger polynomial, of which we wanted to check if its roots are rational. Well, we know algorithms for checking for computing the roots of a polynomial, and even something we can do even faster is computing just its rational roots. And so you see this is exactly what this algorithm does. It takes the same input, the same output, and it computes the Rothstein-Traeger polynomial, so just as the previous algorithm, and then it computes its rational roots, something we can do with a polynomial time in n and log h. And then we check if all roots are rational, then we return algebraic, else we return transcendental. This seems very much easier to do and very much more efficient in practice. Okay. So the complexity is a polynomial in n and log h, and we also have other approach. So one with indicial equations, for instance, that also has a polynomial complexity in n and log h. So I will not detail this, but okay. So we have other approaches that are much more effective. So what we can wonder is why did we do everything that we did? We wanted an algorithm. Now we have an algorithm, but it's not efficient. Okay. So let's see how it runs, so how our algorithm runs on very small examples. So our algorithm here is p-curve, and 3 other approaches are here. Approaches that do not rely on local global principle, or at least in highly effective algorithm. So for instance, here you have factorization. So if we take this input, we compute sigma, and we see that here it is small. So it's actually the smallest sigma we could have for a non-trivial A over B. And even in this case, our algorithm runs slowly. Its computation time is slower than all other approaches we had. And so if we look at these 2 lines, 2 and 3, we see that sigma is much, much, much higher, even though it is quite obvious by just having a look at it that we want them to return algebraic. Because here it's just p prime over p, and here we have rational roots, so rational residues. So here it took 8 minutes to compute, compared to a few milliseconds. It's quite a shame. And in this case, it did not even finish. Okay, but now what happens on the last line? We have a much more complicated rational function as input. We have a much higher value of sigma, but the output will be transcendental, and so now we are competitive. So what happened? What happened is what I said earlier, that to return transcendental on an input, we just want to find one appropriate prime number for which just with one prime number, we can show that something is transcendent. So here probably what happened is that we computed something like the 3 or the 5 curvature, and it was non-zero, and so we could conclude on the transcendence of the equation.
Do you remember, or roughly, the p which is critical for this one?
So I don't remember exactly for this one, but in practice, in all computations I did with transcendental outputs, I never reached p higher than 17. So I really mean it's probably 3 or 5. So, well, yes. Okay. So now 2 observations. The first one is something which is the motto actually of all this work, is we observe that if solutions are not algebraic, then a small p-curvature, so a p-curvature will be non-zero for a small prime p. But okay, this observation might not make much sense because it's actually just a reformulation of our theorem. If solutions are not algebraic, we say that a p-curvature is non-zero for a p smaller than sigma. And you see that sigma sometimes is huge. So what we say of our theorem right now is that it is probably it's probably non-tight at all. Like we expect to have a much smaller bound sigma that we can compute. The second observation is if we compute rational functions with random coefficients, it will almost always return transcendental. And we see that when it returns transcendental quickly. So to compare our algorithm with other algorithms, what we did was do that. We take a degree. You can see we went up to high degrees, and a height. We went up to very high heights. And what we did was say, okay, I compute random rational functions having these parameters, so this degree and the height at most this. And we run many computations with these random examples. And it always returns something very quickly. And you can see that now, when degrees and height increase, we can go much faster than other algorithms. So here it's the approach with the initial equations. And here it's the approach with computing the rational roots of the Rothstein-Traeger polynomial. So something that's hidden also in this is we managed, in this case, to avoid computing the Rothstein-Traeger polynomial. So it went even quicker. But so in the end, what you can take away from this work is that proving transcendence is efficient in the case we treated, but proving algebraicity, well, it's much more complicated, at least with our approach. And so a bit on perspectives, well, it would be to make such a work on all proved case of the p-curvature conjecture, because this was really the first most easy case. And yeah, so make all proved case of Grothendieck's p-curvature conjecture effective. And thank you for your attention.
Yes, questions?
Yes.
Yeah, but also Chudnovsky is a homogeneous result about curves, but not only P1, yeah? In physics, do you have some similar story, yeah?
No, so actually it was a motivation to have this. So indeed in 1985 they proved the Grothendieck conjecture for order 1 equations with algebraic coefficients over curves, and we do not know yet. We want to attack this problem, but we do not have an answer yet.
Because I have actually personal interest in these things with curves. I have a theorem which is when non-effective, consider elements in the group ring of free group and take exponent of sum of traces of n's power divided by n, and takes power n. Then the theorem says this thing is algebraic and it uses Chudnovsky result, but there's no idea of what is the degree of polynomial here.
Yes, Cyril.
So if you compare with theoretical algorithm by Singer, was there some cases for which it was in fact possible to use the Singer algorithm, and or was it always hopeless?
So I actually do not know any implementation of Singer algorithm because it relies on a theorem that at some so it really theoretically from the it relies on very high data, so I do not believe it has been implemented, but maybe I'm mistaken.
And in different parts you were mentioning a basis of algebraic solutions. So more or less the question of, is it the case that all the solutions are algebraic and so on, but in combinatorics we care sometimes for just one branch, for one solution with very specific initial condition. And it may be the case that, maybe, I don't know, that some other local basis won't be algebraic. Is it playing a role in your work, or is it possible to always remove this case?
No, so we're really interested. So if you have a basis of algebraic solutions over Q of x, then all solutions are algebraic. Okay. So, but now there is also indeed other questions, which is, does there given a differential equation, does there exist one or many algebraic solutions? So it's another question that we cannot attack with our approach. And another problem is, given one solution of a differential equation, is it algebraic? And there are results in this, so not from me, I did not work on that, but there are results in this direction from Bostan, Salvi, and Singer from this year.
Okay. Thank you. Other questions?
So we thank the speaker.
Thank you.